In this talk, I will introduce our work, Event Coreference Resolution with Non-Local Information. Event coreference resolution is a task to determine which event mentions refer to the same real-world event. Let's first try to understand this task from this example. 3 journalists at the New York Times announced plans to leave the newspaper. The departures follow moves last month by several other Times employees, all of whom were leaving to join digital companies. We first need to identify each event mentioned. This involves determining the trigger, which is a word or phrase that triggers an event, as well as its subtype. In the first sentence, there are 2 triggers, announce and leave, and their subtypes are broadcast and end position. In the second sentence, there are 2 triggers, departures and leaving. Both of them have subtype end position. We then perform coreference resolution. In this example, event 2 and event 3 are coreferent because they refer to the same real-world event, that is, the journalists leave the New York Times. One major challenge is error propagation. While the trigger detection errors may propagate to the event coreference component. One solution proposed in prior work is a joint modeling, which allows later tasks in the pipeline to influence the earlier tasks. We hypothesize that the power of joint event coreference models have not been fully exploited. In this work, we seek to extend it. The idea is that the better we can model each task involved, the more we can potentially get out of joint modeling. Specifically, we extend the joint model proposed by Lu in 2017 by incorporating non-local information. We propose 2 extensions. The first extension aims to improve trigger detection by using topic information, and the second extension tries to improve event coreference by using discourse information. In Lu's model, each candidate event mention is associated with 3 types of variables. First, we have trigger variables. The value of a trigger variable is one of the predefined event subtypes or null, which indicates that a word is not a trigger. Second, we have coreference variables. The possible value of a coreference variable are the IDs of the preceding event mention or new, which indicate that event mention starts a new cluster. Finally, we have anaphoristic variables. The possible value of an anaphoristic variable are anaphoric or not anaphoric. In our model, we keep the trigger and coreference variables, but replace anaphoristic variable with topic variables. Each topic variable takes a value in a set in which the topics have an one-to-one correspondence with the event subtype labels. Despite this one-to-one mapping, these 2 types of labels shouldn't be interpreted in the same manner, as we will see later. A word-induced topic label is influenced by our supervised topic model, whereas a word subtype is not. Our model defines a log linear probability distribution over these variables. While in this formula, X represents the input document context, Fi represents a feature function, and theta I represents the weight associated with the feature function I. We define 2 types of features. The first type is task-specific features, and the second type is cross-task interaction features. Let's first talk about the task-specific features. For trigger detection, we use the following features: the trigger word, trigger lemma, the background, the information of nearest entities, and the trigger words subject and object. Our first extension is topic model. Recall that we have 19 topic labels in total, including an one-to-one mapping between 18 subtype labels and 18 of the topic labels, and the remaining topic label is other. Each candidate mentioned is represented using 19 features. Each feature encodes the probability that the candidate mention belongs to the corresponding topic. As we can see from this example, the probability of n position topic is much higher than other topics. Although all of those probabilities are derived from the output of a labeled LDA model. Next, we talk more about the labeled LDA model. To train the model, we represent each training document using candidate triggers as well as context words that are used for distinguishing the topics. To get the useful context words, we rank the word by its weighted log likelihood ratio with respect to trigger and subtype. The label set of each training document is a set of subtypes collected from all the triggers in the document plus other. During inference, given a test document, we first apply the model to infer the distribution of topics in the document, and then we compute the posterior distribution of topics given each candidate mentioned in the document using Bayes' rule. We then use this posterior distribution to generate features. Our event coreference model is a ranking model that ranks preceding candidate event mentions. The model uses two sets of features. The first set contains features extracted from the current mention, and the second set contains features representing a preceding event mention and its relationship with the current mention. Our second extension involves leveraging the discourse information to improve this event coreference model. Specifically, we introduce a pre-processing component for event coreference resolution, where we prune the candidate antecedent of an event mention that are unlikely to be its correct antecedent based on discourse context. We try to use this pre-processing step to simplify the job of event coreference model. We encode the discourse context of each event mention using entities that are salient at the point of the discourse in which the event mention appears. The reason we use entities to represent discourse context is that the distribution of discourse entities is a natural consequence of the topic continuity observed in the coherent text. Specifically, we encode the discourse context in this way. We first compute the salience score of each entity with respect to event mention using the following formula. In this formula, entity mention E is a mention that appears either in the same sentence as event mention M or one of the preceding sentences. G is a score that is computed based on the grammatical rule of entity mention E, and the decay is a decay factor computed based on the sentence distance. We then define the discourse context as a list of entities whose salience score is at least 1. We then train a ranker that ranks the candidate antecedent. This ranker employs the same linear model used for event coreference. We define two sets of features, which encode the discourse context similarities. The first set is salience score ratios. For each entity E, we compute the salient score ratio as the ratio of E's salient score with respect to event mention M to E's salient score with respect to candidate antecedent C. For each CM pair, we encode the number of entities whose salient score ratio falls into each of the 5 intervals. The second set of features are lexical features. We generate all the entity mention pairs in M's and C's discourse context. After training, we apply this ranker to prune all but the top K candidate antecedent of each event mention. We prune the candidate antecedent not only in the text set, but also in the training set. Recall that we have 2 types of features. The second type of feature consists of cross-task interaction features. We use binary and ternary factors to capture the task interdependencies. First, we have factors capturing the trigger coreference dependencies, which shows as the red factor in the graph. Each such factor connects 2 trigger factors and 1 coreference factor. Next, we have factors capturing the trigger topic dependencies, which shows as the green factors in the graph. Finally, we have the factors capturing the topic and coreference dependencies, which shows as the blue factors in the graph. For training, we learn the model parameters by maximizing the conditional log likelihood of the training data with L1 regularization. For inference, we use belief propagation. It computes the marginals for a variable or a set of variables to which a factor connects. Next, I will show the results of our model. We perform training and evaluation on the KPP 2017 English and Chinese corpora. We evaluate the event coreference using 4 matrices and their averaged F-score. We also report the performance of trigger in terms of recall precision and F-score. Let's look at the event coreference result first. For English dataset, we use Huang's model, which report the best performance on the English set so far as our baseline. As we can see, our model outperforms on all matrices except blank. For Chinese dataset, we use a participating system in KPP 2017, which achieves the best performance on the Chinese set as our baseline. As we can see, our model outperforms all matrices. Then let's look at the trigger detection results. As we can see, our model outperforms the baseline on all 3 matrices. Similarly, on Chinese dataset, our model outperforms the baseline on all 3 matrices. To evaluate the importance of each of the 2 extensions in the full model, we perform ablation experiments. We first ablating each of the 2 extensions. As we can see, ablating each of the 2 extensions causes a drop in performance for both event coreference and trigger detection. Second, we can see ablating both extensions causes more abrupt drop in performance than ablating one of the extensions. We then explore the effectiveness of the discourse-based pruning. As we can see, the percentage of the correct antecedents that survive the pruning is far greater than the percentage of the candidate antecedents that are pruned. In this work, we incorporate the non-local information into a state-of-the-art joint model for event coreference resolution. and the model achieved the best result to date on the KPP 2017 English and Chinese event called reference cover.